Good. So yesterday where we started, we spoke about convolution. We saw how convolution came about, and then we went through the mechanics of the convolution process, the convolution integral, how to go about evaluating it. And we ended up looking at just in general terms, looking up at a simple problem here where we have two rectangular pulses. Both of them are height 1 and both of them are time width 1. And out of that, there were some things that we realized that we have to look at. And the two things, of course, would be the zones of overlap, and then the what do you call it, the integral integral limits. Right now, when we did that, the zones of overlap had to do with the size of the pulses, and the integral limit had to do with where, when we reverse the pulses, whichever one we happen to be doing the time reversal and sliding with, that determined how the problem worked. So we attempted this one yesterday in broad context. And if you remember when we did it, right, let me just go forward a couple of slides here. When we did it, remember of the sort of important things we saw is that once you have, if you have, just let me get our pen going here. So we have one of the pulses, right, say the X here, and we have the other one, which is H. H is coming along here, and it's the same width. When you flip it around, remember when you H t minus tau, the flipping around, getting the minus tau part is always around this axis here. So you have to look and see how the pulse was. So when we flipped it around, the pulse basically went from 0 to -2. And then if we put the t part, depending on where t is here, the pulse, this part of the pulse will be t now, and this part will be t -2, right? And then we follow through. So let's go and we look at some other examples now in terms of how we establish, well, first off, the zones of overlap, and then the actual integral limits depending on the zones of overlap. So the next one, and again, if you have any questions at any point in time, please call out to me. All right. So here's the second example. We're finding the convolution of H and X. Another example where the pulses are exactly the same width. X is occupying 2 time units. H is also occupying 2 time units, but except it is going from -1 to +1. All right. So the convolution of those two, of course, you decide. Remember from the properties yesterday that X convolved with H is the same as H convolved with X. Meaning one of them, remember the integral, is the integral of X tau ht minus tau, or it could be H tau xt minus tau. So one of them, you look at them and you could decide which is the one you want to keep stationary and which is the one you're going to reverse and slide along the time axis. All right, just again for this case, we will reverse the H function and slide it along. So if ht and xt are as shown, x tau will be exactly the same thing, and h tau will be exactly the same thing that we have here. Flip it around, h minus tau. What's that going to look like? What is h minus tau going to look like? Remember, when you reverse it, you're right. You're flipping it along the t equal to 0 axis. So h tau, let me get a different color here. H tau, h minus tau is going to be exactly this. All right, we are about the 0 axis. So what are the limits now? So if I start to move this and I have h, so I'm doing the convolution here. This is h, and now I have to have t minus tau. Good. Where is t? Where exactly is t located? No, this variable, that t is a span, that's fine. But remember, ht is a variable. T is where we're going to vary to slide it. When we did the example, the first example, this one, when we flipped it around, h was running from 0 to minus 2. This was h minus tau, and ht minus tau, this point became t, and this point was t minus 2. Right? So I'm asking the question for this one now. We flip it around, so this is h minus tau here. Ht minus tau, therefore, is somewhere on the time axis, but where exactly is that, this t bit now? Is that the front of the pulse, the back of the pulse, or somewhere else? Right, to answer that question, ht is actually, when you flip it around, let's go back to the, at t, when I had this pulse going from 0 to 2, when I flipped it around, the front of the pulse was 0 and the back was minus 2. So in other words, wherever I was in the time domain, if I put this to point 1, this was the front, this was actually where t was. In other words, it is where the h0 point is where the t variable becomes. So h0 was right here. When I flip it around, it stays right here, so that the h0 point, when I move it around the place now, t and 2 minus t, sorry, t minus 2. If I ever want to bring it back to the origin, if t equal to 0, it comes back to where I started, which is when I flipped it around on 0. So in this case here, if I want to bring this back to look like the original pulse, when t is equal to 0, it means that t has to be here, right in the middle, exactly as it was originally. So this point, the front of the pulse, will be t plus 1, and the back of the pulse is t minus 1. Make sense? Right, okay. So let's repeat. We go to the blank page here. I just clear that page a little bit. So I have this is my original pulse. This is a previous example. So we're running from 0 to, let's say, 5. Right? Change this from t to tau, I haven't done anything, it's still going to look like that. H minus tau is now going to look like this, right? So I flipped it around, but where is the H 0 point? The H 0 point is right here. So when I have this, which is H minus tau, if I shift this around to now some arbitrary point on the x-axis, t minus tau, right? When I put t equal to 0 here, I'm supposed to get the front of the pulse landing up to where it was originally. So in other words, if I put, when I shift this around now on the axis and I'm somewhere, let me just use a slightly different color. If this is somewhere here, this point is going to be t, and this one is going to be t minus 5 units behind. So where's t0? Where's h at t equal to 0? T equal to 0 is here. Sorry, t equal to 0 is here. So that when I put that in back into the pulse actually goes back to where it was supposed to be. Yeah? Make sense? So now, if I have h looking like this. So minus plus 2, sorry, to minus 2. H tau is that. H minus tau is going to be exactly the same thing. Where is H0? H0 is here. H0 is here. So if I now shift this along the time axis to some t minus tau, t minus tau is here, whichever this point is. So the front of the pulse, right, will be t plus 2, because 2 this way, and the back of the pulse will be t minus 2. Yeah, this is the t point here. Forget it all. Sorry, there's a t point. I've shifted it to the position t somewhere arbitrarily on the axis. Make sense now? Yeah? No? Maybe?
So
Right.
excuse me.
Mm-hmm.
So basically, right, the T point, when we shift it, we would to locate back the T point on the pulse is basically wherever it was when it started, wherever it was before. So for example, if T is equal to 0 was at the right hand side of the pulse, or say the front of the pulse, when it is
Mm-hmm.
shifted, I want to find the T point again, it would be on that location.
Correct. In other words, wherever they whatever the axis, when you reverse the you're always reversing it around t equal to 0, right? Whenever you go from h tau or x tau to h minus tau, you're flipping it around the t equal to 0 point. So when you shift up and down the axis, that is the point that is actually going to be moving up and down. So you need to know where that is in relation to the pulse itself. So for argument's sake, and I would actually going to come to that later, if I had something looking like this, ah boy, come on, behave yourself. Let's say this was h tau, right? I've already changed from t to tau, right? And this is, let's say, 4, and this is 3. h minus tau, remember, is going to be flipped around the 0 axis. So h minus tau is going to be this, is going from -3 -4, right? But the t0 for this is here. This is t equal to 0. So this point is actually t minus 3, and this point is actually t minus 4. Yeah?
Understood. Understood.
Okay, so the important thing, what you have to keep track of is, first off, where's the origin in terms of the either x or h, whichever one you happen to be flipping around. And then once you put it on the x-axis and you slide it, well, the t-axis, I should say, sorry, and you slide it along t equal to 0 is wherever it is going to be to bring the pulse back to its original place. So you need to locate that, and then the pulse is measured from that point. Now notice what will happen. This affects the other thing I was telling you about earlier on. This affects the limits of integration. When we start to overlap, this will affect what the limits of the integration are. Okay, so that's an important consideration to remember. So if we go back to here then, if I am going to solve this, did I start here? No. So if I'm going to solve this, so h minus tau is going to look like exactly the red pulse here. H t minus tau. All right, so if we bring it on the axis here, the 0 point t is right in the middle here. So this part is t plus 1, and this part here is t minus 1. So now, what are the zones of overlap? Remember, I told you there's two things that we have to look at. First, you have to look at the zones of overlap, and then the integral limits. So as we're finding the convolution here of x and h. H is the one I'm moving along the time axis. So as h moves along the time axis, h is moving along this way. Right? What is the first? As it slides along, as t continues along the place, the first point is when t plus 1, when this line t plus 1 is just less than 0. Yeah? So for t plus 1 less than 0, you have no overlap. Agreed? Yeah? Right, so for t less than 1, we have no overlap. In other words, and you have to put that down, that is t less than minus 1, there's no overlap. Okay? The next piece of the next part of the equation, let me clear that, sorry, will be when something like that. This is t plus 1. This is t minus 1 here. Right? So the next part now, when it starts to overlap, is this overlap zone here. And that point is t plus 1 greater than or equal to 0. Remember, we say we change at the, we use the greater than or equal. In other words, once it's less than, nothing happens, but we change at the transition, at the time point. At t plus 1 greater than 0, right? That's the first point. And you have to know what the back, if the front of the pulse is doing something, the back of the pulse is following right behind. At the same time, and t minus 1 less than 0. Because as t plus 1 goes forward, t minus 1 coming up behind. All right? So This, remember, and this is a moving thing. This is not a fixed. A lot of people look at it and say, okay, this is a fixed point. Remember, t is varying. I'm continuously varying t as h slides all the way along the time axis from minus infinity to plus infinity, right? So it's a continuous thing. So at any point in time, we can determine what the convolution is. So right now, at this, I'm taking a snapshot. So for this scenario where the pulse is now moving, where the h pulse is now moving over the x pulse, sorry, as they overlap, the range now where there is actual overlap at this point, these two scenarios, and I combine that to get t less than 1 and greater than or equal to minus 1. And what are the limits now if I have to do the integral? The actual limits of integration of the overlap, the limits of integration, the lower limit is what? Where's the overlap actually taking place from? Where are the two things? Look at the red line. The lower limit is here. Remember, this is x. X is starting here, and t is here at this point in time. So this zone is going to get bigger as the pulse gets. So the lower limit is 0, and the upper limit is t, wherever t plus 1 is. All right, the front of the pulse, remember, is t plus 1. T plus 1. Yeah? So 0 and t plus 1. And it is for this zone. So the zone of overlap, the second zone of overlap is this, and the limits now, and then of course x, whatever x tau is, and ht minus tau. It just so happens that both of them are 1, right? We'll have another scenario in a while when they're not. So everybody clear with that? I mean, it's just, it would be nice to work this out on a marker board, but at least hopefully the writing is clear enough. Right, and that continues. Let me click some of this mess off. That continues merrily along until we have total overlap. And then the next zone now is when h does this. Remember, this is t plus 1. This is t minus 1. So zone of overlap is now here. Right? So let's see what the limits are. The first thing, of course, you always have to do, what is the limit of this zone? What are the limits? This now is t plus 1 greater than or equal to 2, and t minus 1 less than 2. Work out that, you should get, when you combine them, you should get t less than 3, right, on greater than or equal to 1, somewhere between 1 and 3 now. Notice how wide is this zone? How wide is that zone? 2 units. And how wide are both of the pulses? Both of them happen to be 2 as well. So somewhere inside, whenever you're doing this thing, as a check, somewhere in the overlaps, you must have a zone that is the same width as one or both of the pulses. All right? We will see later on when the pulses are not equal that it actually, one of the zones has to be the same size as the smallest pulse. So if you're not getting those kind of numbers coming up, then you have the limits wrong. And so now that you have a zone, what are the limits of the integration? The lower limit is going to be, look at the yellow shade. So what's the lower limit? T minus 1. And the upper limit, yes, is 2. And you integrate x at tau multiplied by ht minus tau again. Right? Notice that the answer is always, in this case, a function of t. And if you can visualize it, if you just visualize the shaded part, if I were to put the shaded part, if I was to plot the shaded part as a number, right? What will happen is that at some point in time, you have no overlap, so the shaded part is 0. Then that shaded part increases to some maximum. That is when the two pulses are one over the other. And then like this, remember, H is doing this. So that shaded part is now going to get less and less, and eventually is going to come back down to 0 and then go on. Right? So we had the first zone, no overlap. We had the second zone that we just did. This is the third zone. So the fourth and final zone for this will be when h t minus tau is like this. So this is t plus 1, and this is t minus 1. So the final zone is when t minus 1 is greater than or equal to 2, which is t greater than or equal to 3. And they do not overlap at that point in time, so that the answer for the convolution there is 0. Right? Fair enough?
So for the third stage, I kind of miss how the overlap was 2 units when t was between 1 and 3.
Okay. I can't go back on the slide, but I can draw it again. Right, so you have t plus 1 here, and we have t minus 1 here. Right, so the zone, the overlap zone is here. And that, the time limit now is t, oops, let me get a better color than that, t plus 1 greater than or equal to 2. But t plus 1 has now gone past that point, and t minus 1 less than 2. Remember, t minus 1 coming up behind here. Put that together, you get t less than 3 or greater than or equal to 1, right? Which is a 2-unit overlap, which makes sense. Just think about it. The h is 2 units wide, and x is 2 units wide. So as it starts to overlap, as h moves from here, right, it's going to increase this whole thing and then eventually decrease. So as it covers over x, this is a 2-unit span. It's going from 0 to 2 here according to x, but the limit, as we saw where t is, but it's a 2-unit span, right? 2 units. Oops, there's 2 units. Yeah? Make sense?
Yeah, it makes sense now. What I was looking at was the actual yellow part shaded in between from 2. And
No,
I was
that's
saying,
right. Right. The yellow part is the overlap, is the actual part where you're going to do the
the
integral. And you
integration.
start to do it, right. So those are the limits, right? That is the limit of the convolution itself, but it's not the limit of the zone of overlap. Remember, this is now, this going to give me a function of t, right? That function of t will run from t equal to 1 to t equal to 3. So at any point in that 2-unit overlap, I could figure out what the actual convolution value is. But the integral now, at this point, the function of the integral is this area. This is the variable bit here, right? Remember, the integral is a variable thing, right? It's a continuous sum, if you like, that is a function of t. So at the end of the day, I get some function, which is t plus 4, just for argument's sake. So if let's say that the result of the integral was t plus 4 after I did the mathematics, then the lowest part at t equal to 1, it means that the convolution was 5. And at t equal to 3, the convolution was 8. Right? That's all it means. So x convolved with h was 1 at t equal to 1, and 3 and 8 at t equal to 3. That's all it means.
All right, understand now.
All right. But listen, well, yeah, you have the chance, I guess, now is a good thing. Apart from reading the notes, you can actually listen to the recording again and see if what I'm saying is making sense. You also have to try it with pen and paper as well to sketch it out. Take some paper and you write the thing out a little bit. Draw some scenarios like we're doing here, and see exactly where those limits, where the upper limits are, where the lower limits are, and how they affect the zones of overlap. So that was what I was saying early on, that in all of this thing is gone now. But I said that the important thing was that you had to find out, one, the zone of overlap. So in other words, where they actually are, what is the area of interaction, so that they could calculate the product. And then using that now, you have the integral itself, and then what are the time limits for how long does that zone of overlap exist, right? So just to go back here, that zone that we just did, the one going from t equal to 1 to 3, t equal to 1 to 3 starts here. That is when that zone of overlap now starts and ends here. And this is the back end of the pulse, right? So it begins here, and as t moves along, it ends here. So the front of the pulse, t plus 1, crosses over. It goes all the way over, and eventually the convolution ends when t minus 1 passes over. And if you want to and look at about it again, just do a different color here. When t plus 1 passes, look at t plus 1 alone. Forget the back of the pulse. T plus 1, as t varies, is going to do this, until eventually the whole pulse is overlapped, right? And there's 2 units. And then it's going to move away, and the back end now is going to go and do this, and do this, and do this. So the area goes up to a maximum and then decreases to a minimum again until eventually the pulse passes. And that's another 2 units, right? So the convolution actually is a 0 units when they, for zone 1, when they don't, what do you call it? They have no overlap. 2 units when the convolution is increasing. That's when the front of h t minus tau is dragging across x. 2 units again when the back of h t minus tau is dragging across x. And then nothing again when the pulses are no longer overlapping. Yeah? Make sense?
Makes plenty sense.
Right? And you could do it, it's easy. I mean, two pieces of paper could help you out. Two post-it notes, for instance. Those will be identical sizes, so you can see when one passes over the other, right? So nothing happens until they overlap. They pass over, then full overlap, and then it decreases again, and then you're back to nothing. All right? So that's the first, those sort of scenarios with identical pulses. The next bit of fun that we have are when the pulse is not equal, right? And that adds, so let's have a case like this. Let's try to get this working here. This misbehaves every so often. So this is X, and this is H. X is going from 0 to 1, just for argument's sake. H is going from 0 to 2. Right? So you want to find a convolution of these two, you take the same, you have to do the same thing. You're picking one to reverse and slide, whichever one is up to you. And having done that now, of course, if I were to use the convention, let's flip the H for the time being. Right? So if I were to flip the H minus H tau is exactly the same thing. And H minus tau will be flipped along the, what do you call it, the t equal to 0 axis. So it's going to run from 0 to minus 2. So this is H minus tau. And Ht minus tau will now be any arbitrary place on the axis. The front will be t, and the back will be t minus 2. So this is Ht minus tau. Yeah? And now we go and we attempt the convolutions again. So the zones, so once you have that, so the first part is to figure out whichever the pulses I'm reversing, and then to figure out where the front of the pulse is and where the back of the pulse is. And we go through the process that we just did. So the zone of overlap will now be, the first thing is, if I put that here. So the zone of overlap, we have X. So this is X going from 0 to 1, and Ht minus tau is t and t minus 2. Right? So this is Ht minus tau, and this is X tau. So as we see, the first zone of interaction, or no interaction, sorry, is t less than 0, right? So we have nothing. T less than 0, we have nothing. Then what is the next step? The next one will be when this moves here. So we have t here, and we have t minus 2 here. Right? Now, this is where a little bit of difference comes in. How big is pulse X? Pulse X is 1 unit, and pulse H is 2 units. So, as we move t along the axis here, the first, my next zone of overlap is t greater than or equal to 0, which is here, as we're moving. Remember, the back of the pulse is coming up, but what is going to happen is that t is going to approach 1 before the back of the pulse gets anywhere near 0. Remember, H is 2 units wide. So at this point in time, t is going to reach 1, but the back of the pulse, which is t minus 2, will still be outside of the overlap zone. So in other words, this particular area of overlap will be t greater than or equal to 0 and t less than 1. That's because the two pulses are not the same size. X is smaller than h. Yeah, which is t less than 1 less than or equal to 0. Following? All right. Make sure you understand this. So if something isn't clear, let me know. Or when you listen to the recording or you happen to review it again, let me know. So that's the next, and then, so that's the first zone between t equal to 1, between 1 and 0, greater than, what do you call it? Less than 1, greater than or equal to 0. And what will be the limits of integration? The overlap zone is here. So the limit of integration will be the lower limit is 0 and the upper limit is t, sorry. Right? And you work it out, whatever x and is, it's x and x of t and ht minus tau, whatever those two happen to be. Good, so we're sliding along literally. And so we draw this again. So we come back with x, which is 1 unit long, and we have h, which is this now, right? So this is t, and this is t minus 2. So at some point when t gets bigger than 1, we have this situation now where the whole of the pulse of x inside or subsumed by h. So what is the zone of overlap? The zone of overlap is this entire thing here. Right? 0 to 1, very good. And what is the limit here? This is, at this point in time, the limit, the time zone limit that we're dealing with is t greater than or equal to 1. Remember the other one was between 1 and 0. T greater than or equal to 1. And we have the back end of the pulse now, t minus 2 less than 0. So what that's going to give me? T between 2 and 1 now. And the upper limit here, now notice what is going to happen. This one, this area is going to remain the same size for a little while. It remains, let me see if I can draw that again. This is x. So that overlap zone is going to remain, it starts here, right, when t is just here, and it ends here. Sorry. Do I have an eraser anywhere in here? I know what I'll do. Let's get back to red here. This is x here. Right. So that that particular little overlap zone starts here and remains the same until it's there, and then up until the point where the back end of the pulse does that, you realize that the zone of overlap remains constant for that period of time. Right, so if you could imagine H sliding here, it's totally overlapping X for a period of time. And the overlap zone is between 0 and 1. In other words, that particular area of overlap is a constant for a period of time. Everybody seeing that? Just if you try to figure it out right here, and if you're not understanding, take a legal size piece of paper and a letter size piece of paper, and as you slide, if you pass the legal size over the letter size paper, right, at the start to the end of the legal paper, the overlap is only this area of the letter size. It's like a shadow on the letter size that the letter size paper has, and that will remain so for a little while. So inside of here, you're going to have a constant area for a while. So this particular area of overlap will be not a function of t, but a fixed value. And then the back end of the pulse, now we start to see what happens now as we continue the convolution. T minus 2, this point is going to start overlapping, and then the overlap zone, as we go forward, is going to get less and less. The integral limits are going to be between 1 and t minus 2 now, and then eventually nothing. So what you're going to get now, when the before, when we did the two pulses being equal, we had 4 overlap zones. Remember, there was the 0, then a zone where they were, it increased our maximum, right? So that was one zone. Then another zone where it decreased our minimum, and then another overlap, right? And all of these were functions of t. Nothing, this was a function of t, this was a function of t, and nothing. In this case now, we're going to have a 0 overlap zone. Then we're going to have one where it's increasing, which is a function of t. Then we're going to have a constant zone that is going to stay fixed. Then we're going to have another one that is a function of t that is going to decrease, and then it's going to go back to 0. Yeah? Following? Anybody not following? Of course, sometimes you have to listen again to the lectures, watch the slides, and sometimes the best thing to do too is to actually draw the scenarios and figure it out. So this one now, this is the second sort of scenario which the pulses are not the same. One is bigger than the other. So you're going to have this fifth zone here that is going to be created. Sorry, what am I doing? This zone here, where you have a constant area of overlap. So the convolution, if you want to look at it graphically, will do nothing. It will increase to some value. It will stay at that value for a little while, and then it will decrease and go to 0. Whereas if what we did before, when the two pulses were the same, it came, it went up to our maximum, it went down to our minimum, and then it went back to 0 again. Right? So this constant zone here is as a result of one pulse being bigger than the other. So that there will be a period of time when both pulses overlap. Right? And then, so if that wasn't enough to contend with, so we have two equal pulses, we have two not equal pulses, right? We have, so let's clear this one. And what would happen now if I had, right? So I have X looking like that. and then h looking like this. So x going from 0 to 2, and for argument, h going from 2 to 4. So h tau will look the same thing. H minus tau is now what? H minus tau looks like what? Right, there we go. So h minus tau, we're going to have minus 2 here, minus 4 here. And ht minus tau means because the t0 point is here, so the front of the pulse is going to be t minus 2, and the back is going to be t minus 4. So this is ht minus tau. Yeah? And once you have that correct, then you can start to do the zones of overlap. Regardless of how big h or x is, the first zone of the no interaction will be t minus 2 less than 0. At this point here, less than 0, right? Or t less than 2, all right? And then the next one will be t minus 2 greater than or equal to 0, and t minus 4 less than 0. And so you go on. The two pulses are the same size here, so how many zones of overlap you expect? Or how many zones you have to at least evaluate? Right, there will be 2 zones of overlap, but you actually have to evaluate 4, right? You remember there's a 0 zone, count that. Then 2 where there's overlap, and then there's a 0 zone with no overlap. So always count that. So there's 4, 1, 2, 3, and 4. If h or x was bigger than the other one, you're going to have a 5th zone, right? So you'll have the no overlap, you'll have the variable zone 1, then you'll have the constant zone, then you'll have the variable zone 2, and then the no overlap, all right? Just like we did for the previous case. Yeah? And then we have this. And all the variations of this. Now, this one is the most complex of the lot that you will encounter for 2 sets of things. One, this pulse. The pulses are equal, and of course, we could have all sorts of scenarios. You could have the scenario with this is the pulse and that, or I could have scenario like that where one is equal and one is square and one is a larger triangle and the like. Right? But the biggest issue now is, you remember all the time we were doing the integral x tau h t minus tau. For all of them, x and h were 1. They happen to be 1 between t equal to 0 and 2 and that kind of thing. Here we're going to have a scenario now, and we need to find out x is not 1. X is that behavior here. So what is x? How would you go about defining x? What kind of signal we call that? We looked at that in one of our earlier lectures. Well, yeah, triangle, right, okay. People getting cute. I was thinking about it in terms of, no, it's not a sawtooth. It's triangle, but the triangle pulse is something called piecewise continuous. Remember that? It's piecewise continuous because it has this behavior. Then at this point in time, it changes to that behavior. So we have to define x in two parts. There's a part for x between 0 and 1, and there's a part of x between 1 and 2. So let me see how good you remember your add maths. What is the equation for x? Between 0 and 1. Y equal to, well, we're dealing with t, so it will be y equal to t, or x equal to t, right? So this bit here is nice. X equal to t. What here? What's that bit now? You sure about that? If x was minus t, it means that t equal to 1. Both lines intersect, right? At t equal to 1, I will get two different values. So x is not minus t. Don't guess. Right, so you have to remember, what's the slope? You have to go back to your little calculus here. I have a piece of a line that is running between 1 and 2, and the slope is minus 1. So what's the equation of that? Nope. Correct. X is minus t plus 2. All right, so this part is minus t plus 2 or 2 minus t, however you want. And the checkpoint is at this point. At x equal to 1, according to this line, at x equal to 1, this point is 1. According to this line, at x equal to 1, that point is 1. So that is correct. Right? Here, it is 0. So at t equal to 2, it is 0. That is correct. And of course, at t equal to 0, it is here. So x, therefore, x is equal to t between 1 for t less than 1 or greater than or equal to 0, and is equal to 2 minus t, right, for t less than 2 and greater than or equal to 1. Wow, 2. Yeah? So see, don't jump. That's one of the things as where people make little mistakes that will throw you off. So you use that, and part of the evaluation of the convolution expression is that you have the correct equations to start with. So this one is a little more complex. You have to make sure you know the correct, and don't assume just because it is symmetrical. If one is xt, yes, the other one has a slope of minus t, so it's minus t, but there's a constant because it's not passing through the origin. Right, so you have to remember that, and then once you work it out, check again. The two lines have to intersect at the point 1, 1. So at 1, 1, you have to get the same answer from both parts of the expression for x, both parts of the whatever equation is defining x. And then after that, now the process is the same. Now, if I were to give you this and tell you to find the convolution of x and h, it's still easier to flip h around on the t-axis than it is x. So you would keep x stationary and slide h over it. And this one now is a little bit more intricate because of the discontinuity here. So when you're evaluating the zones, remember that x changes function at this point here. Right? for some reason I'm crooked, I'm offset. So x changes its equation at this point here. So when you're doing the overlapping, so for instance, if I have this and looking at this will be the front of the pulse and this will be the back of this particular pulse. If I have to evaluate this zone of overlap, and the zone of overlap is this entire range here in blue, notice I have to evaluate it from 0 to 1 because x has a particular behavior in that zone, and then between 1 and t because x has another definition between on that side of the pulse of that side of t equal to 1. Yeah? Everybody following? Yeah? And then they sort of more complicated, and you'll see that in a couple of, there are variations of this that I have in the problem sets that I've given from time to time. So you will see x look like this, or h, I could do either one. You will have x look like that, right? You can have x or h look like that. You can have x or h look very wide, but everything is always the same. The first thing you do is to define the equation of it. It's just a line, right? I'm not giving you any expressions that are involving curves at this point, because the idea is for you to understand how to evaluate this mechanically. And you'll see why later on, as I mentioned before, some of these things, although we know from the Laplace domain, and remember the convolution lecture is really part of that whole thing. We know that the convolution of these two is just hs multiplied by xs. What is hs for something looking like this? hs for something looking like that, if you remember when we discussed piecewise continuous signals, if you had to find hs for this is a unit step. So the answer is going to have a transform of a unit step. This is a unit step. And then we have a constant in the middle. So to define a pulse in terms of the Laplace transform involves having two unit steps in there. So you're going to have a 1 over s for the first one, and another one, a delay here, is going to be a 1 over s, and s minus something because of the 2, right? S minus something around the place here. So that is on this part. What is the Laplace transform of this? That's piecewise continuous. So to evaluate the Laplace transform of something looking like that, from what we did, you have a step function here, because that's where it's increasing. Or in fact, no, we could probably do this a little bit. It's still not. We have a ramp. We have a ramp, but the ramp starts here and then it ends. We have to have a ramp and a step. Then we have to have another step and a negative going ramp here, right? So 2 steps and 2 ramps to define xs, right? Every step is going to give you something with a 1 over s. Every ramp is going to give you something with a 1 over s squared. And on this side, we had a 1 over s. We had 2 1s over s, 1 over s plus and another 1 over s here. Right? Some b1, b2 over s. And this one would have a s plus a at least on it because it's delayed. Right? Same thing on this side. So you're going to have an s, you're going to have a 1 over s, a 1 over s plus or minus a or something like that. And then a 1 over s squared and another 1 over s squared with a sign because it's a negative ramp and the like. You have to multiply the two of them, get the partial fractions, do the inverse transform, and convert it back to time. Which do you think is the easier one to evaluate? Or which one you'd rather do? Yeah. Rather do it mechanically or doing the Laplace transform. The Laplace transform is not good if you have to evaluate systems that have piecewise continuous signals in them. We saw that every piecewise continuous signal involves the creation of a step function in there. And every time you have a step function, then you have the Laplace transform of that becomes part of your whatever you're discussing, right? So many cases like this, it's easier to actually evaluate. If the system is going to be subjected to something like this, then it's easier to evaluate it mechanically. And we're doing this not so much because I wanted to test you out to see how much integration and so on you know. Later on, when you're doing controls, you're going to meet systems where there are pulse responses, and it's not a simple thing to sit down with paper. So you're going to have to what do you call it? Model the system, approximate the system, and there are ways you could do it with straight lines like we're doing now, and you can get a ballpark idea of how the actual system will work. And if you ever do discrete signal processing with me in year 3, using a computer and using some simple algorithms is very easy actually to evaluate the convolution. It's something that the discrete time convolution, which we introduced this whole topic on, discrete time convolution is very easy for a computer to do. It's just a series of multiplications and additions. So it is in fact something you can convert a problem like what we have in front of there into a discrete time version and actually evaluate it, even in something like Excel. You use a spreadsheet and you could actually do it. It's a multiply and add process, right? The continuous time is multiply and add, but it's just that the continuous time summation is integration. Yeah? So everybody fair on that? There's a lot of material in terms of the various scenarios that we covered today. All of it boils down to basically 3 things. One, you're looking at the zones of overlap. 2, you're looking at the integral limits. And maybe even before the zones of overlap, the first thing, the equations. What are the equations that define x, t, and ht? If they are plain rectangular pulses, that's fine. If they happen to be pulses whose height is not 1, well, they're just constant. So instead of 1, it will be 5 or 6 or -2 or whatever it is. But the instant they are not pulses, you have to find the equation that defines either h or x. And look at them carefully. Right? Don't assume because they're symmetrical that the equation of one side is just minus the equation of the other. So the first thing is to define the equations. The second thing is to look at the zones of overlap. Draw the thing out and draw the scenarios where whichever one is the function that you're going to reverse and slide. Draw that and move it along the other one. Use pencil and paper is easy, right? Or if you like the computer and thing, just draw one and slide it over the other one. You could cut and paste it and move it along the place and see what happens. And then the third thing is that having established the zones of overlap, look now at the integral limits. Yeah? And the variations were, of course, that the pulses are equal width, that they're symmetrical about the time axis, that they're not symmetrical about the time axis. One is either before or after the time axis and so on. And then one of them is not a rectangular pulse. Yeah? Lots of material, and the second problem set has some questions on that as well too. So at this point, I will, well, let me take some questions before I end today's class, because I wouldn't start another topic. I want you to think about this. There's a lot of material that was covered here. We spoke a lot, but there's a lot of things that I want you all to make sure and look carefully, and come back to me with a question if something doesn't make sense or something isn't clear. And it will only happen to when you start to do some of the problems in the problem set as well. Look at that. So any questions? at this point? Of course, we'll go over the tutorial. So I just have to just look for the time. I think we have a slot. We are supposed to have a slot after in the afternoon, or I will take one of the 1 hour of the 2 hour classes and go over that. Yes, we will go over the tutorials. So I'll see how best we can, but you all need to at least attempt the problem sets first, and let's see if maybe by next week we could have the first tutorial. Yeah. Yeah, but I hope other people as well started. Don't let the material pile up. It has a way of getting accelerating fairly quickly. Because after we finish here, we're going to look at the behavior of first and second order systems, which ties back a little bit to the Laplace transform behavior as well. And then from there, we're going to do block diagrams. And then after that, now, up to block diagrams is where the midterm usually is up to. And then after that, now, after the midterm, we spend a couple weeks on the Fourier series and the Fourier transform. Then we talk about some stability issues on both plots and the like. And then we go into the discrete domain and we talk about the Z transform and finish it off. So this is some of this stuff was, well, this is all new stuff, but the Laplace review that we did was something that you did before. So have a look, the first two problem sets will sort of tidy up everything that you have. We'll have the tutorial and then this sort of newish material, the real new material starting, well, we've started already and we're moving forward from here now. All right? So keep up with the material, and if things are not clear at any point in time, always feel free to contact me or to raise the question in class. Okay? So everyone all right? So far at least? Yeah? Right. Okay, so that's good to know. As a heavyweight boxer said, everybody has a plan until they get hit. So keep up with their work so that when you get hit with a midterm joke, you don't go all awry. So anyway, let me end the recording now.